Okay, hello. I'm going to be making videos basically explaining concepts and doing practice problems for dynamics, first year dynamics for engineering students. So basically, this is the formula sheet used at my university. So I'm going to be following this. What we didn't learn was this stuff though, down here. We didn't ever do this, so I won't be doing it either. If your university does, you won't find me teaching anything about this here. And also, we didn't really go over this stuff. We did go over it in the notes I'll be using as a reference, but not like crazy in depth. So don't expect the greatest of teaching for principles of angular impulse and momentum, and then no teaching at all about whatever this stuff is, translating and rotational axis for relative motion, because we didn't do that. Anyways, how these videos are going to work, there's going to be two parts. One where I just type out the notes and explain stuff, and then another where I will be doing practice problems so that you can actually see the process of things and how the equations will work. The first unit is really easy. It's like a high school review basically. It's this stuff here, these formulas. So these videos will probably be a little shorter, but the fundamentals are important to know for everything else in this class. And quickly, I want to go over notation. So for derivatives, I'm going to be using prime notation because that's easier to type. If I wasn't lazy, I could do LaTeX, but I don't want to learn LaTeX. So we're not going to do LaTeX. Anyways, let's begin with the actual notes itself. So there are four quantities that are going to be the fundamentals to this course. There's position, time, mass, and forces. Okay, position, this is easily defined as just a point in space, and it can also describe size. So point in space describes size. Time is pretty obvious. It is a measurement of things moving along in events, succession of events basically. Measurement of the succession of events. Mass is the amount of matter that influences how objects behave relatively to each other. So the amount of matter that affects the behavior of objects relative to others. So for example, that would be like gravity. The mass of one object exerts a gravity on the mass of another object. Obviously that's really minuscule on like the scale of on Earth, but if you go into space, that scale is a lot more important. But we don't need to worry about space stuff. That's just whatever. And then forces, this is pretty easily defined. Mass times acceleration. Acceleration is just meters per second squared. But it can also, it's like the push or the pull from one body to another. That's what a force is. Push, pull from one body to the other. All right, so those are the four fundamental quantities that are in mechanics. So for each of the problems in this class, there's going to be some assumptions we make that will just help with all the calculations to make everything easier. So there are two that apply to the entire course. Oh, my spelling sucks. There's two that apply to the entire course, and then one is going to be cut off near the end at one of the last few chapters. All right, so for the entire course, we have that bodies are rigid. So we're doing rigid bodies for the entire thing. So there's no decomposing, there's no like deformations or anything on the body. They're just going to stay completely solid and still the entire time. And then the second assumption for the entire course is that loads are concentrated. So the forces, basically what this means, I'll draw this one out. Let's say we have this wall, right? So a force hits it here, force F hits it at this position. Normally it would like distribute out, but for this course we assume that it's concentrated at this one position. So instead of multiple force arrows like you might see in first year statics, you would have loads that are distributed across a section. For this, we're only going to have the one load concentrated right wherever the force is at. And then this last assumption, which ends at chapter 10, we're on chapter 1 right now for reference. It ends at chapter 10, is going to be assuming that particles, or assuming that the thing we're studying, and by studying I mean like the subject of the problem, is a particle. Particles are subject of study. So that means that it has mass, but the size is negligible. So we don't care about the size of what we are studying. And that assumption ends at chapter 10. So it runs from chapter 1 to chapter 10, this assumption. Okay, so that is the introduction to the course. So next we need to go over units of measurement. Units of measurement should be pretty easy. These are all fundamentals. There are 3 SI units. So I'll be doing everything in SI. Sometimes imperial units will come up, but I don't like imperial. I don't know anyone who likes imperial. So we have length, which is meters, but in imperial it is feet. We have time, which is just seconds. Everyone knows time, that doesn't matter. And then we have mass, which is kilograms for metric and slugs for imperial. I didn't actually know slugs were a thing until I took this course. So that's something fun to learn. We also need to know unit conversion. So like the prefixes, if you have like a gigameter, that's 10 to the power of 9 meters, right? So you need to know those. There's giga, mega, kilo, milli, micro. This takes the mu notation. Wait, let me get my thing. Oops, that's not the right app. I don't know if I have this. Yeah, there's mu, and then there's nano, which is just the first letter of the word associates with it, and the capitalization was done on purpose. Like nano is lowercase n, that's why I left it as a lowercase n. Micro is just the only one that is has a mu instead of the actual letter, so that's why I did that like that. And then next up, there's something called dimensional homogeneity. Dimensional homogeneity. This is a pretty easy concept, but it's basically saying each side of the equation has to have the same units, right? So if we have S, this is not seconds, by the way, S is distance. So if we have S, one of the fundamental equations we have right here, right? S equals S naught plus V naught T plus half AC T squared, right? That is one of the fundamental building equations for kinematics. So we have S equals S naught plus V naught T, right? V naught times T plus half A T squared, right? Like that. So if you were to actually go through all of the units, right? We have S is meters per, or is just meters, right? S naught is again meters. V naught, right, is meters per second, but we're multiplying V naught by time. Time is in seconds, so that becomes just meters. Same thing for half AT squared. I'm too lazy to write that out, but it's the same thing. It's meters per second squared times time squared, which is second squared, becomes just meters. Both sides of the equation are in meters. So whenever you're doing a question, make sure you check your units. That's extremely important. Anyways, significant figures. I'm sure you all know significant figures, probably from chem, old physics courses. No one likes them, but we're always going to be using 3 significant figures for this course, right? That's all there is to it, unless the question specifies otherwise, obviously, but just stick to 3 significant figures. It is very, very simple. Okay, now unit conversions. You will sometimes have to switch from metric to imperial, or like do nanometers to millimeters, or whatever the question needs, because you want your calculations to all be in SI for the most part. There's some exceptions, like if you can get everything to be like kilo, then you can keep your unit, you can keep your values in kilo. But for the most part, you want to be doing your work in SI units, and SI is what's listed here. These are the SI units. So yeah, for the most part, you want to be sticking to SI units, but there will be some unit conversions from imperial to metric. For example, I'll just do one, but for force, we have it is pounds, right, for imperial. And this is equal, 1 pound is equal to 4.448 newtons, which is metric. This is force from imperial to metric. This is a conversion that you will probably be, depending on your professor, they could be really evil and make you memorize this or something. But if it's needed in the question, it will probably be provided to you, this information. So I don't think you need to memorize it. I wouldn't personally, but that's fine. Okay, on to the next part. Now we're going to be actually starting the course, basically. This is like all the build-up, all this stuff. This is the prerequisite stuff that you should already know. Okay, this might be new, because, I mean, who's converting to imperial ever in their life? But other than that, that's all you need to know. So let's begin actually with rectilinear. Oops, that's not how you spell that. Rectilinear kinematics. Okay, so kinematics is studying motion. So that one's pretty obvious. And rectilinear, that means a straight line. This is rectilinear. This is not rectilinear. Okay, that's pretty obvious. So we've already defined our 4 fundamental things here. But we're going to now take position, and we're going to mix with time, and we're going to define them more clearly. Position, displacement, velocity, like all these things. So position, we denote with S. That's what we use for position. This is the exact point where something is. That's what it means. If we have an axis, we have a point. This is its position. Point AB, or whatever it is. 4, 5. If that's, yeah, it looks like 4, 5. So that's position. And position can be defined as a vector, right? So vector notation is this number I, or it should be I hat, but I don't want to do that. J hat, K hat, if you're in 3D, right? This is a position vector of, or this is a unit position vector. But yeah, it can be a vector, or it can just be like, I don't know, a distance. This guy is 5 meters away. That's a position. Next up is displacement. This is basically position, but we use delta S to denote displacement. So there's a difference here. Position is just S. Displacement is delta S. This is a change in position. For example, he walked 5 meters, and then he walked backwards 4 meters. What's his displacement? 1. 1 meter is his displacement. Let me visualize that. So we have this guy up here. He walks over here 5 meters. He walks back 4 meters. What is his displacement from the origin? Right here, 1 meter. His displacement was 1 meter. 5 minus 4. Right? S2, like position 2, minus position 1. Or something like that. Position 1 minus position 2. Yeah, I reverse that. whatever. So that's displacement. It is a change in position. It's a vector. Oh yeah, I probably should have brought that up. Vector and scalar. I expect you already to know that, so I'm not going to explain them. Displacement is a vector. Yeah. And then there's velocity. Okay. Velocity, which is v. V is the, the variable, or whatever, the symbol for velocity. This is in meters per second. This is a change in position with respect to time. Speed, I guess more accurately, it would be delta v, right? Because speed is v. So this is change in position with respect to time. This is just position with respect, something like that. I don't know. Yeah, it's the speed is the magnitude of velocity. Sorry, that's what I meant to say. It's the magnitude of velocity. So if you have like -4 meters per second as your velocity, the magnitude of that is just 4, right? Because magnitude is absolute value. So the magnitude is, yeah, that's what speed is. And then velocity and speed are basically derivatives. S prime, right? ds dt is equal to velocity. So S prime is equal to velocity. You need to know these derivatives, by the way, and we have it listed here as well. V is ds dt. I guess you could see as well. A is dv dt. That's whatever. So velocity is S prime, which is equal to V. Same thing with speed. And then we have acceleration. Acceleration, which we denote with A. So this is meters per second squared. This is the change in velocity with respect to time. So V prime is equal to A. And you can also say S double prime is equal to A, right? Because if velocity is a derivative of position, displacement, and then that means the velocity again, so double derivative of position will be acceleration. So that's all that stuff. You can get rid of time actually, because these are derivatives with respect to time, right? So if I actually write out the actual notation, we have dv dt is equal to A, and then we have ds dt is equal to V, right? You can eliminate time from these equations to get this form. A is equal to ds, ADS is equal to VdV. Because if you were to just take the derivative of this, or yeah, you get them equal to dt, so ds over v equals dt, and dv over a equals dt, right? Now you have two equations that are equal to each other. ds over v equals dv over a. And then you just rearrange the formula, you get a ds equals v dv. This one is, I'd say, intuitively pretty obvious, because when you integrate acceleration with respect to position, you're going to get your velocity, right? So you can also think of it like this is graph stuff. Like, I'll get into graphs later, but there are graph stuff that you need to actually know. You need to know the relations for graphs. Okay, so now these are your quantities for kinematics: position or displacement, velocity, acceleration, and time. You find time in the derivatives. And these are all functions of time, by the way. Like it's S is a function of time. You denote it like that. Or that's how that's my function notation. I know some places have different notation for functions, but I use this one, like f of x, or s of t in this case. So that's function notation. These are all functions of time. So time, accelerations, velocity, and position, those are your kinematic quantities. Okay? Now, we're going to start off with constant acceleration. So that means a as a function of t is just equal to a, or a sub c for constant. C is constant. That's what we're starting with. Just constant acceleration. All right? So there are three equations that come with constant acceleration being what is in the question. So for example, if your question is like, find the velocity of this ball that has an acceleration of 5 meters per second squared, that's constant acceleration, which means you don't do any integration stuff and no derivatives. You're just gonna use these formulas, right? So the first one, and just for a quick distinction here, because I don't want to keep writing like subscripts and stuff, I'm going to put a slash next to something if it means not. Like, let me see. You see here, this is v naught. I'm gonna write that as v slash because I don't want to write sub 0 every single time. That just looks ugly. So I'm gonna put a slash. Oh, I guess it's division. Whatever. You'll get used to it. So v naught equals v slash. I can do a other direction slash, or no, wait, that is the other direction slash. Yeah. This slash, that's not division because this one's division. Yeah. Oh, I didn't know this was a thing. Whatever. I don't use that. Anyways, so our first equation, we have velocity is equal to v naught plus a. It is a sub c, but I'm not going to write that. Plus a bracket t minus t naught. Okay. Where this v is final velocity. This is initial velocity. This is constant acceleration. This is time. This is t naught is your initial time. Basically like when the constant acceleration starts. So if you have a question that's like here, we're driving our car. This is a car. Don't question the shape. You're driving your car. Here it has acceleration t, right? It's a function of time. But then at t equals 3, it becomes constant acceleration of 5 meters per second squared. So you would set t naught. This is your t. This is t slash. This is t naught, for example, right? So back to it. That's equation 1. There are derivations for this. I could go over it if that's something people are interested in. But you basically just take these equations, these relationships, and you would just do some integration with them to get to these equations. That's all there is to it. You would take these and like this relation, integrate them, and that's how you'd get these 3 equations. These are the 3 kinematic constant excel equations. But yeah, that's how you would get these. Next up, we have one for position. So position is equal to s naught plus v naught t minus t naught plus half a t minus t naught squared. Okay. We already went over this equation earlier over here when I was explaining dimensional homogeneity. So, but this is for position. You have final position at the front. This is initial position, initial velocity, time, initial time, constant acceleration, time, initial time squared. Right? And then the final one is v squared is equal to v naught squared plus 2a s minus s naught. Final velocity, initial velocity, constant acceleration, position, like final position, and initial position. That's what this is. Okay. So those are the 3 equations you're going to be using when you have constant acceleration for a kinematics problem, right? Now something we need to discuss actually is a datum. So I'm just going to pull up pulley problem. For example, right, just a random pulley. If you have this, I just want the image. Open image in new tab. There we go. So if you have this, let's just take this and then zoom in a little bit. There. If you have this, right, you might be thinking, where would I want to study it? And this is where we use a datum, right? So a datum is just taking it, a point, not a point really, a line. Oh, that's offset. But a line across your your body or whatever you're studying, this is not a body, this is a system. Your system, a line across your system of wherever you're studying, and you're basically setting this as your origin, right? So you're saying with respect to this origin, this is going towards the origin. So I would call this negative. Like these tensions, I would call these tensions negative. And then that would mean my force of gravity is actually downwards. So down is positive in this case. And then you would be like, find, what do we got? Find t prime. That would be what the question's asking. So a datum, you want it to be a fixed point, which means there's like nothing variable happening about it. Like this one, this is a variable point. You have 3 forces on this. 1, 2, 3 forces, right? This is a fixed position. Like this can move. Like this block can move, this string can move, and then this can move, meaning that this thing will like rotate in like one direction or something like that. This one, you just assume it's not moving because of like equilibrium stuff or whatever, but it's fixed to the roof. That's like your biggest indicator. If it's fixed to like the roof, a wall, if it's just fixed in place, this is going to be your datum. You can see this is stuck to the wall. So you would put your datum, I always draw it through the hole, just not this time because the pencil thing's unaligned because I zoomed in. But I'd always draw it through the hole in the center of the pulley. I don't think it really matters. It just looks nice. But this is where you would set your datum. That's what a datum is. Again, if that needs further explanation, just let me know in the comments or whatever. And now we go on to erratic motion. This is where the graphs come in. So this is what erratic motion is basically. You can't represent any of your functions. So s of t, v of t, a of t. This is when you can't represent them with one clean function. So like maybe you have this, right? A, oh, that's an ugly A. A and t, and this is your acceleration, right? That's not one function. I don't know what this is. Maybe some parametric function could make this, but we're not doing parametrics because no one wants to do that. So you have 3 graph types. Let me get lines here. Okay, 3 graph types. We have S versus T. So S of T, V of T, A of T. You can also get like, there's 2 other graph types because, okay. You can also have these functions, V as a function of S and A as a function of S. So those are other functions you can have, right? Anyways, so this is S. T is just across this whole line, so I'm not going to bother rewriting it. And A, V and A, and then T, T, T. So you could have S versus T graph that looks like this, right? I know this looks like it's one function, but like imagine it isn't. At this point, let's just switch colors here quickly. At this point, you would have a slope, which is ds dt. So S prime is this slope. And then you'd have points. This is T1, T2, T1, T2. And then these correspond to S1 and S2, right? So this is not the path of the particle. Keep that in mind. Like you might think, oh, this is a path, but no, this is just like how far away it is from wherever our origin is at a given time. So like at time 2, we're saying the thing is, let's just call it 10 meters away from us. And then at time 3, let's just put time 3 here, it's 2 meters away from us. That's what we're saying. This is not the path. It's not saying the guy traveled this direction. No, it's just saying this is his distance. We could do the same thing with like a velocity graph here, like this. Okay, and this dip's negative. Again, you have your slope at the. You have your slope at this point. This is v prime, which is okay. This slope here. This is the velocity of the particle. This is the acceleration of the particle. This slope here, acceleration of the particle. Again, you'll have your T1, V1 stuff, and then T2, V2. Let me put, let's just put T2 here. T2 and V2 here. And then in between this, so the area under the curve, this is the integration. This gives you, this is the position. Or the displacement, sorry. This is the displacement of your particle in this moment. This is an integral that just gives you s. This is s right here. And then if it's above the x-axis, this is positive displacement. And if it's below the x-axis, this is negative displacement. If you know anything about graphs and integration, that should be pretty obvious. By the way, this is like trying to keep in line of plotting one particle. So anyways, I need to extend this so that it becomes negative. And then, yeah. Okay, there we go. And then we have this, which is just like that. Again, we have T1, A1, T2, A2. Oops. T2, A2. And then let's grab our blue again. If you integrate this, this gives you the velocity. Yeah. Integration signs matter and stuff. This is pretty easy graph stuff. You need to be able to read a graph that's provided to you. For example, if you have like a multiple choice question, there'll probably be graph. There will be graph questions. I can guarantee that. But you need to be able to read an ST, VT, AT graph, and you need to be able to tell something. You need to be able to read a value from it. Like if it says, what's the displacement, and it gives you a VT graph, you need to be able to know, I need to take the area of the curve. Like, okay, for example, you could get a curve that's like this. This is VT, right? And it says, what's the displacement of this particle? Let's say, you know, value 1. Let's say this is 3. This is 0. This is a triangle. Area under the curve is pretty easy for a triangle. It's just the areas of a triangle. Half BH. Yeah. So the base is 3. The height is whatever. This is 5. So 15 over 2, 7.5. There you go. That's your displacement, 7.5 meters. Right? That all makes sense? Okay. Now there's, again, 2 more graphs. So let me just draw those out quickly. Graph 1, graph 2. Wow, those are not straight lines. Okay. This is a VS and then AS. So VS like that. And then AS, I guess same shape, yeah. Again, we have the same things. DVDS, it's like the slope. The slope across here. This is DVDS, which is acceleration. The slope of this is nothing. Okay, there is stuff that is like the derivative of A. I don't know if it's for, I know for time. I don't know if these functions are a thing for when it's a function of position. So I'm not going to even mention them. I could have brought them up earlier. But like, again, if you integrate this, this gives you the velocity. So that's graphs. That's how graphs work. Pretty easy stuff. And that's all for this video, the teaching video. There's going to be a practice problems video that like actually uses these equations. But I hope that all my explanations were good. Thank you for watching. Bye-bye.